In this video, we're going to talk about one of the important consequences of anthropogenic climate change. That is the increasing heat content in the ocean. A lot of attention has been paid to the increase in near surface temperatures. Turns out about 90% of the excess heat caused by anthropogenic warming has gone into the ocean. So by anthropogenic warming, I'm talking about the warming that's caused by humans putting CO2 and other greenhouse gases into the atmosphere. This figure shows the total accumulation of energy in joules, 10 to the 21 joules, so that's a 1 with 21 zeros after it. A big, huge number. But what's important really is that we're looking at 0 being the state in 1970, and on the bottom axis we have time from 1970 up to 2012-ish. This is a stacked plot, so the total energy is a combination of upper ocean, deep ocean, ice, land, atmosphere. So the total over time is this black line here, and the uncertainty is between these dashed lines. So at this point, there's fairly large uncertainties. And as we get closer to the present, we now got more instrumentation, more observations, so the error bars get smaller. The light blue here is the upper ocean, so the top 700 meters of the ocean. And you can see that phenomenal amount of the excess heat has gone into this upper ocean. The dark blue here is the deep ocean, so below 700 meters deep. And again, that contribution is growing. So between the two blue ones, the two ocean ones, we have about 90% of this excess heat. And we have heat going into melting ice, the gray line through here, going into heating up the land. And then this purpley color that you can barely see down here is excess heat going into the atmosphere. So now if we have a closer look at the heat content in the ocean, the upper left-hand panel shows the warming trend in the top 700 meters, so the lighter blue color in the previous plot. The color scheme here is degrees per decade. So reds are warming areas and blues are cooling areas. The fastest warming is happening in the North Atlantic. There's some reasonably fast warming happening in the tropical North Pacific. And then South Pacific has a bit more either not warming or potentially even slightly cooling. The upper right-hand plot in this figure is the warming in the deep ocean, so below 4,000 meters depth. The colors are again in degrees Celsius per decade. The reds are warming and the blues are cooling. You'll notice here that the warming is starting in the southern hemisphere. It's starting in the Southern Ocean and then moving up into the various basins. And this is because of the deep water formation around Antarctica. So we have warming up to about 50 milledegrees in parts of the Southern Ocean. And then as you move into the Pacific, that drops down to maybe 2 or 3 degrees Celsius per decade. And in the South Atlantic, probably more like 4 degrees Celsius per decade. The plot in the lower right-hand corner here shows the warming rate as a function of depth from 1,000 meters to 6,000 meters. The orangey line here shows the global average, so the average over the entire global ocean. And you see that as you come up to 1,000 meters depth, you have greatly increased warming, and then it's actually going to continue warming faster as you get up into the upper ocean. You have essentially no warming around the 2,000 to 3,000 meter depth. Then below that, you get increased warming rates again. The purpley colors show the Southern Ocean, so just an average over the Southern Ocean down here. You can see that in the Southern Ocean, the warming rate is quite large compared to what you see at similar depths in the deep ocean in the global average. So what we can take away from this is essentially what we can see in this plot above, that at the deeper depths, the Southern Ocean is warming the fastest, and globally, it's the upper ocean that's warming fastest. An important consequence of the heating of the upper ocean is an increase in stratification. So by increasing the density gradient at the upper ocean, you're making it harder for nutrients or pollutants to mix down deep into the ocean. What this plot shows is the density stratification on this axis and then latitude on this axis. The lines are zonal averages, so at a particular latitude band, you average all the ocean around there. So equator in the middle, North Pole over this side, Antarctica here on the left-hand side. The brownie line is the historical stratification, so that's observations from 1996 to 2005, and not surprisingly, it's higher stratification in the tropics. So in the tropics, we have the surface ocean warming up, we have a very shallow mixed layer, and then the 200-meter depth is below the mixed layer. So quite a temperature change over that depth range in the tropics. When we get into the mid-latitudes, we have less of a difference between the surface and 200 meters depth. Also shown on this plot are two different scenarios for the future climate. So the blue line here is a scenario where there's a fairly aggressive decrease in the amount of CO2 that we put into the atmosphere. And then the red line here is a worst case scenario. It was designed as a worst case scenario, but it's pretty close to the business as usual scenario. So you can see that under both future scenarios, we have an increase in stratification in the tropics, quite a big increase in stratification under the business as usual scenario, less of a difference in the mid-latitudes in the southern hemisphere, and then still quite a difference in the mid-latitudes and high latitudes in the northern hemisphere. So you could see that in particular in the North Atlantic in the previous plot, where we had quite a lot of warming of the upper ocean. So the surface of the ocean is going to warm first. And so we'll end up with an increased stratification over those top couple hundred meters. This is a figure from a recent IPCC report, which shows extreme events in the last 20 years that can be associated to an increase in heat content in the ocean. So over here we have the 2014 hurricane season in Hawaii, where we had 3 hurricanes in a row. We have lots of hurricanes in the Gulf of Mexico and the Caribbean, and a decrease in the extent of the sea ice minimum in the Arctic, and a decrease in the volume of sea ice in the Antarctic. And then a number of places around the ocean, so around the Pacific, both sides of the Pacific, around the Atlantic and the Mediterranean, Indian Ocean, we have marine heat waves. Marine heat waves are defined as periods where the ocean is in the top 1% of the observed range from the pre-industrial period. So if we look in a bit more detail at some of the heat waves in the last 20 years, in the left-hand plot, the colors are the maximum temperature anomaly that was observed during that heat wave. So some of them are up to 6 to 8 degrees warmer than normal during the heat wave. The shading of the boxes show whether or not the heat wave has been shown to be directly attributable to anthropogenic climate change. The white boxes are where the analysis hasn't been completed yet. So in these cases, you can't rule out that there's a link to anthropogenic climate change. So in the Pacific, we have heat waves all the way along the Alaskan coast and west coast of North America. We have heat waves around Australia, up to Papua New Guinea and New Zealand, and then in the North Atlantic up around the Labrador Sea. So the most famous of these heat waves was the blob, which occurred in the North Pacific up here, the Alaskan Bight, and down into the west coast of the US. So this had impacts over the land, so changes in weather systems over the land. It had impacts on marine ecosystems, and it had a financial impact on humans. The right-hand panel shows what's called degrees heating weeks. So this is the amount of heat that's accumulated over a 12-week period. So you can see that the degree heating weeks are high in areas where we have marine heat waves. So the blob in this area along the equatorial Pacific, around Australia and New Zealand and Southeast Asia. The colored dots indicate the consequences for coral reefs. So the dark colored ones that are the most common ones in this figure around Hawaii, Great Barrier Reef, where there's severe consequences or severe bleaching of the coral reefs. In the Caribbean, there was some severe bleaching, and there were a number of places where there was either moderate bleaching or no substantial bleaching. As you probably know, corals can recover from a short-term bleaching event, but prolonged bleaching events will lead to long-term damage of the corals. So if we look at a time series of the potential occurrence of these marine heat waves, here we have pre-industrial and then all the way up to 2100. The vertical axis is the probability ratio. So here we have that they occur the same rate as pre-industrial. Here they're 10 times more likely than they were in the pre-industrial period, up to 70 times more likely than in the pre-industrial period. The gray line here is a simulated historic record. The black line is the actual observed historic record, observations. And then we have the two scenarios we talked about earlier. The aggressive reduction in CO2 on greenhouse gases, and then the business as usual case. So you can see by the end of the century, if we don't change the amount of greenhouse gases that are being emitted, marine heat waves will be 50 times more likely than they were during the pre-industrial period. And if we aggressively change our behavior, then we can probably cap them at being less than 20% more likely than they were in the pre-industrial period.